Hello, today we are going to discuss the process of equating redox reactions using the electron-ion balance method. It is important to note that this procedure can be quite complex, but the method itself yields highly accurate results, particularly when dealing with complex redox reactions. Take, for instance, the reaction scheme presented here. However, it is crucial to understand that the redox reaction in this case occurs in a specific medium, namely sulfuric acid, making it an acidic medium. In this acidic medium, the reaction equation can be arranged in different ways. For instance, the acidic medium can be positioned on the left side of the equation, while the right side will always yield water. Alternatively, the medium can be inverted, resulting in water being on the left side and the acid on the right side. Despite the arrangement, it is important to acknowledge that the acid will always be present either on the left or right side of the equation, as is the case in this scenario where it is on the left side. It is worth mentioning that the reaction equation provided is not yet equated, and it is currently in its molecular form. Step 1. We need to convert this molecular equation into an ionic equation. What do we do to do that? We determine which of the given substances are strong electrolytes, and they will dissociate. Those substances that are not strong electrolytes will be weak or non-electrolytes and will not dissociate into ions. Then those ions that are reducible, we will not write into the ionic equation. The formula potassium 2, chromium 2, and OVEC is a strong electrolyte salt. Salt and potassium are all soluble, so potassium No2 will also decompose. Sulfuric acid will also decompose. Potassium ESO4 is an electrolyte, potassium No3 is an electrolyte, and chromium ESO4 is a triple electrolyte. But water will not decompose. It's a weak electrolyte, so what you end up with is chromium ioside with a charge of 2-, plus No2-, plus No3, minus, plus chromium with a charge of 3+, and then there's water. So which particles have changed shape or charge? It would be chromium 2 OVE changing to chromium and No2 changing to No3. Step 3. We need to write down two half reactions. The first half reaction is chromium 2 O7 minus changing to chromium with a charge of 3+. The second half reaction, No2- transforms into No3-. The next step in this process is to balance the half reactions. Currently, there are 2 chromium atoms on the left side and 1 on the right. To correct this, we will place a coefficient of 2 in front of the chromium on the right side. However, the second nitrogen half reaction is not balanced. We need to ensure equality. Moving on, the next step involves modifying the equation to adapt it for the appropriate environment. Currently, there is oxygen on the left side but none on the right. In order to remove the oxygen, we can add hydrogen ions if the medium is acidic. Once the hydrogen ions are added, the reaction on the right side will produce water. On the left side there's 7 oxygen, on the right side there's 1. We put 7 here, then there are 14 hydrogens here. We put 14 in front of the hydrogen formula. Next step, for No2, here we have 2 oxygen, here we have 3, oxygen is added. Consequently, on the left side we add water, and on the right side we get hydrogen ions. Oxygen we have 3 here, on the right side we have 3. Hydrogen is 2, we have 1 here, so we put 2 here. We've made a half reaction. Now we have to determine how many electrons are involved in the process. On the left-hand side, in this case, we've got plus 12, on the right side plus 6. So it turns out that we have chromium reconnecting 6 electrons. In this case, the charge on the left side is minus, and on the right side it is plus. So that increases the oxidation state, so we're going to need to give up 2 electrons. Let's write it down like this. Next step, we put the number of electrons we found behind the line, and then we change it crosswise. In this case, the numbers are reduced. The process of reduction and the element chromium is the oxidizer. The second process is oxidation, and NO2 will be the reducing agent. Next step, we have to make a final equation related to our ions, taking into account the multipliers obtained. At the beginning of the left-hand side, the first multiplier is 1. Then we get chromium 2O7. 2 minus plus 14 plus. This is the first reaction of the left side. The second reaction, we have a multiplier of 3. Therefore 3, when we combine NO2 with 3 molecules of H2O and account for the electrons involved, the total comes to 6. The number of electrons decreases here, causing their size to shrink. We start with 12 electrons, but after the reduction, we are left with only 6. Next is the second part of our reaction. We get 2 chromium, 3 plus plus, 7 H2O plus 3, NO3 minus and plus 6, H plus and plus respectively, will give up 6 electrons. Now, we need to see if there is a similarity in this case. As we can see, we have on the left side 14H plus, on the right side there are 6 of them. What we need to do then, where there is less we take away, and here we leave the difference and we get 8H plus, and it will be only on the left side. What else is similar? This is water. Water on the left side is 3, water on the right side is 7. It's less on the left side, we take it away, and here we leave the difference 4. We can also see that we have the number of electrons that are accepted and given up between each other equally. So our balance is correct, because the number of electrons on the left and on the right in this equation should be equal to each other. Now let's put our found coefficients into the original equation we were given. Chromium 2O7, so potassium 2 chromium 2O7 remains with a coefficient of 1. We don't write the unit. 8 in front of H+, but we have sulfuric acid has 2 hydrogen. So since there must be 8 hydrogen in front of the sulfuric acid formula, we put 4. 3 NO2, so 3 potassium NO2. On the right hand side, 2 chromium, we've got 2 chromiums here. 4 water, so we put 4 in front of the water formula. 3 NO3, so 3 potassium NO3. Now let's check our equation. On the left side of the balance, potassium did not participate in the balance itself. We check on it. Potassium on the left side is 2 plus 3, 5. Potassium on the right side is 2 plus 3, 5. The acid residue CO4 did not participate in our case. Here it is 4 CO4. Here it is 1 and 3. 4, and automatically oxygen in it is also equalized. Now we check by oxygen to make sure that we're going to have the oxygen number correct here. And we get 7 on the left hand side. If necessary, you can write down the number plus 6 plus 1629 to check its validity. This number tends to be quite large, equivalent to 29 multiplied by the element oxygen. By checking to the right, you will find that when 4 plus 9 plus 12 plus 4 is added, the sum is also equal to 29. Therefore, our equation remains valid. The electron-ion balance method in itself is quite a laborious process, but it provides us with the capability to equate complex redox reactions. Therefore, it is important to fully comprehend this method. In our latest lesson, we examined how this method functions in an acidic environment. In our next lesson, we will focus on understanding how these processes occur and how to balance such reactions in an alkaline medium. Farewell.